Alright, so in this video we're going to take a closer look at mixtures of gases. So we have different types of gas molecules in the same container. What can we say about their partial pressures? And the mathematical relationship we use for this came from the observations that we call Dalton's law, or Dalton's law of partial pressures. So just a quick reminder, this experiment is where we've got some container of gas molecules. We keep the volume and the temperature constant. We swap out some of the molecules, say molecules A for molecules B, but we keep the total number of molecules the same. And we measure the pressure, and we see that the pressure doesn't change. So swapping out one type of molecule for another doesn't change the pressure, which makes the calculations very, very simple. If we've got mixtures of gases, we can treat them just like if we had a pure gas, and we can say some things now about the individual gas molecules or types of gas molecules inside the container. Okay, so from the ideal gas law, the first thing we can say that is if N total equals the number of molecules of substance A plus the number of molecules of substance B plus the number of molecules or number of moles, I should say, of substance C, etc., then we can just say P total equals N total RT over V, and we can then say something about the partial pressures based on the numbers of moles of each component. So the pressure exerted by molecules of substance A is just going to be pressure exerted by A. So the partial pressure of substance A is the number of moles of substance A, RT, over V, where this is the total V, and so forth for, say, the other types of molecules. So the partial pressure of substance B would be the number of moles of substance B, RT over V. Again, that's the total V, because our molecules of B are spread throughout the total volume, just like our molecules of A are spread throughout the total volume. And I've got, C's in here because this wouldn't matter no matter how many different types of molecules we have in there. The total number of moles is going to be the sum of the individual numbers of moles of each type of gas in our container. And so we can summarize all this and say that the total pressure exerted by a gas mixture is the sum of the partial pressures of its components. So the total pressure is just the partial pressure of A plus the partial pressure of B plus the partial pressure of C and whatever other molecules happen to be in the container. So let's look, for example, at the partial pressure of all the different substances that are in our normal air that we breathe. Air is mostly N2. The partial pressure of nitrogen molecules bouncing around in the air is 0.7808 atmospheres. The partial pressure of O2 molecules bouncing around in the atmosphere is 0.2905 atmospheres. We've got quite a bit of argon, so 0.0093 atmospheres, a little bit of CO2, 0.00038 atmospheres, and a few other things that don't even show up in this decimal place, and so they don't really factor in. If you add them all together, you get a total of 1 atmosphere. So you might notice something interesting here. We know that the percent of nitrogen in the air is about 78%, or you probably remember that, and that's just the partial pressure, 0.7808 atmospheres of nitrogen over the total pressure, times 100%. That gives us 78.08% nitrogen. And that's by numbers of molecules or numbers of moles. So it looks like partial pressure is just another way of essentially measuring concentration. So let's take a closer look at that, at what it means when we say the partial pressure. And then we'll go back and do a couple other calculations of partial pressures. So like we just showed for the nitrogen, partial pressure, so say PN2 over total pressure, P total, is just a measure of the concentration of how much gas is there. So for N2, that's 0.78 over 1 atmosphere. So it's 0.78 nitrogen, or 78% nitrogen in the atmosphere. But since we also know that, the partial pressure is just the number of moles times RT over V, and the total pressure is the total number of moles times RT over V, then if we take PI over P total, the RTs over Vs are going to cancel out. We're going to get that the partial pressure over the total pressure is just the number of moles of species I of some substance over the total number of moles. Okay, so that's why we call it a concentration. And we actually have a name for that unit of concentration. And we call that unit the mole fraction. So it's just the moles of component I over the total moles in the mixture, which we've said is equal to the partial pressure of substance I over the total pressure. So rearranging this, or just clarifying it again, we have mole fraction equals partial pressure of I over total pressure, and therefore we can say the partial pressure of a substance is going to be its mole fraction times the total pressure. And then there's one other important point, which is that the mole fraction of all the compounds in a mixture has to add up to 1. That's because if you add up all the different numbers of moles of all the different substances divided by the total, well, these individual numbers better add up to the total. So you better have that your sum of all of your different numbers of moles in your mixture divided by the total number of moles in your mixture, that equals unity. So x1 plus x2 plus x3, or xa plus xb plus xc, or whatever, all of them added together, if you have all the different compounds included, it better equal 1. And we can go back to our example of all the different gases in air. So if we add up the partial pressures of all of those, it comes up to 1 atmosphere, because our total pressure is 1 atmosphere. So if we add up the partial pressures of all the components, it needs to add up to our total. So let's start with a fairly simple example. Let's say we have a flask and it contains gases A and B. So there's our flask and it's stoppered, so nothing can get out. And we've got molecules of A and we've got molecules of B in there. And the total pressure is 2.2 atmospheres. We've got 2 moles of A and 5 moles of B. And we want to know what is the partial pressure of gas A in this container. Well, we just said that partial pressure of A is going to be equal to the mole fraction of A times the total pressure. The mole fraction of A is just going to be 2.0 moles over, so that's our Na, over the total number of moles. So we've got 5 plus 2, so 7 moles total. And our total pressure is 2.2 atmospheres. So our partial pressure of A is just going to be 2 over 7 times 2.2, or 0.62, I got 628 or 629 atmospheres. If we want to do that to the right number of sig figs, it would be 0.63 atmospheres of molecule A in that flask. And so what would our partial pressure of B be? What would have to be our total pressure, was P total minus PA, right? Because it has to, our total pressure has to be the sum of our partial pressures. So, sorry, I forgot to pause it when I was doing the erasing there. So to do the total pressure, we have to have just the sum of the partial pressures. So PA plus PB. So again, we know PB equals P total minus PA, or 2.2 minus 0.63, so we get 1.57 atmospheres for our partial pressure of B. Okay? Okay, so now let's change this problem a little bit. Let's say we don't know how many moles of gas A are in there. We know that the partial pressure of gas A is 0.63 atmospheres. And let's say we still have a total pressure of 2.2 atmospheres. Oh no, let's change it. Let's change it. Let's say we have a total pressure of, let's say we're at STP. At STP. And we want to know now if we have a volume of 158, now I'm messing up my problem, 156.8 liters. Now how many moles of gas A would that be? So let me rephrase that problem one more time a little bit more clearly. So there's our question. We know the partial pressure of gas A in our mixture is 0.63 atmospheres, but now we've got it in a 156.8 liter container at STP. How many moles of A are present? Take a moment, pause this, and answer this question using the ideal gas law. So whether it's partial pressure or total pressure, it still follows the exact same principles. So we know the number of moles is going to be pressure times volume over RT. Here it just happens to be the partial pressure instead of the total pressure. And so the P here isn't actually going to impact us at all. It's STP, but we only need that in order to figure out the temperature. We already know what the pressure is. Since it's STP, we would know that whatever else is in there would have to be at 1 minus 0.63, or let's see, 1 minus 0.63 comes out to 0.37 atmospheres now of our other substance. So that means if it's just A and B, now PB is 0.37 atmospheres in this mixture. But we don't need any of that because we just need to know about A, and so it's 0.63 atmospheres times our volume, 156.8 liters, divided by, we better have R in what units? Liter atmospheres, right? Liter atmospheres per mole K times our standard temperature, which is 0 degrees Celsius or 273.15 Kelvin. So if we work this all out, we get 4.49 moles of A, or to the right sig figs, that's 4.5 moles of A. Now that's a lot of moles of gas, but if we think about it, it makes sense because we have a really large volume, right? So big volume would be a large number of moles. And we know there should be about 22.4 liters per mole, and so that comes out to be about right with that number of moles in that volume. Let's look at a problem that's just a little bit more challenging and completely doable with everything that we know about gas laws. So now let's say we have two flasks that are connected by a tube, and there's an opening between these that we can plug or unplug depending on what we want to do with these gases. And I'm going to make it, try and draw it as much to scale as I can. So we're going to say that the volume in these tubes is approximately 0. So we're going to neglect the volume in the tubes. Here's our little stopper. We can plug the passage between the two flasks. And we're going to put molecules of B in this flask 2. And in flask 1, we're going to put molecules of A. And we're going to say that we know and let me color code this a little bit better. So we know that the volume of flask 1 is 1.50 liters, and we know the pressure initially in flask 1 is 0.38 atmospheres. And in flask 2, we have a volume of 2.50 liters, so it's a little bigger, and an initial pressure of 0.56 atmospheres. And the question is, when we go ahead and we remove the stopper, oops, I didn't mean to delete my tube, but we're going to leave the tube connected, but we remove the stopper now so the molecules can mix. So the A's can move and the B's can move. And the question is, after mixing, what is the final total pressure, and what's PA and PB at the end? So keep in mind, as you're doing this, that these are the initial values before we open the stopper, and down here we have the final values, okay, after we've opened the stopper. I'm going to give you guys some time to work on this, so pause the video, see if you can set up this problem and solve for the final total pressure in this system. And then I'll give you a strategy of how I would work through it. Okay, so hopefully you've taken some time, tried to set this up yourself. If you're not done yet, pause it again and keep trying it yourself, because you're going to be a lot better at solving these kind of problems if you've tried to work them through yourself before you watch how I would do it. So if we're trying to find the total final pressure, we know that it's going to be P total is going to be partial pressure of A plus partial pressure of B. And we can group that all together and say that's the number of moles of A plus the number of moles of B times RT over V. Now, the problem is we don't know T, right? We're not given T in this problem, so we cannot use T, so we have to cancel it out. Okay, so we need to come up with an equation that allows us to cancel out that T. Well, we know that the number of moles of A is going to be the same at the beginning and the end, right? And it's going to be at the beginning, the pressure in 1 times the volume in 1, those initial pressures, divided by RT. Again, we don't know RT. And we know the number of moles of B is going to be equal to the pressure in 2 times the volume in 2 over RT at the beginning. So if we plug that back into our equation, then we end up with our total pressure being our P1V1 over RT. Oops. Let me erase a little bit here. Plus P2V2 over RT times RT. So there we go. Now we can cancel out our RTs, which we don't know T, so we got to do that. And that's going to be divided by our total volume, right? We're trying to find the total pressure. We want to know, once these gas molecules have spread through the entire volume, what is the final pressure going to be of everything? So we've got to have the total volume here. Okay, so if that makes sense to you, go ahead and plug the numbers in and see what you get. Maybe pause this and I'll work through it and I'll show you what I get. So simplifying that down just a little bit, we've got P1V1 plus P2V2 over V total. We've gotten rid of all the N's and R's and T's because they're essentially constant. So we can plug in our 0.38 atmospheres, that was our initial pressure over here, our initial volume over here of 1.5 liters, then our 0.56 atmospheres, which is our P2, times our V2 of 2.5 liters, and then our V total on the bottom is just the sum of the volumes of the two containers. We've said we've either accounted for or neglected the volume in the tubes. Now we better make sure that our units are going to come out right. We want units of pressure in the end. So you have liters on the bottom and liters times atmospheres on the top. And so yes, our units are going to work out. So we're going to have 3.28 liter atmospheres on the top, 4 liters as our total final volume. And so we get a final pressure of 0.82 atmospheres in our container as a whole once everything has mixed together. And when I look at this number, I automatically say, does that make sense? And I look at my original numbers and I say, no, this makes no sense. So I must have done something wrong. And I see what I did wrong already. So good opportunity to say, why do we check the answers at the end? We've got 0.38 and 0.56. I can't have a higher pressure than the pressures I started with in those containers, because that would kind of mean that I was adding more molecules or something. So this is actually not right. So what did I do wrong? Well, I actually plugged in a plus sign in my calculator instead of a multiplication sign at one point. So my number here should be 1.97 liter atmospheres. And if I divide that by 4, which is the correct total volume, I get 0.49, and I've got 2 sig figs, so 0.49 atmospheres. And that is between my 2 starting pressures, so that does make sense. That does check out. So it's a good thing that I went back and looked at those initial values to make sure my final value made sense. So now I can go back and solve for my partial pressures PA and PB. I got to be careful. I cannot plug in just that initial pressure there. That's not going to help me because I want the pressure in the entire container. So again, I need NART over V total now. So the number of moles of just A over the total volume after everything's mixed. I know the total volume, so that's my 4 liters. But I don't know T still, right? So again, I can plug in for NA what I do know, which is I know something about it from the initial values. So I know that NA is going to be P1 V1 over RT. My RT is staying the same, so that's going to cancel out, over my V total. And I'm not doing any kind of circular logic here because I had some initial values and now I'm comparing them to my final values. And I'm just using my initial values to figure out what was my initial number of moles. That's what this is here, right? So I have P1 V1 over V total. And maybe you saw that automatically from the last problem that that's what it was going to be, or the last part of this problem. So we've got 0.38 atmospheres times 1.50 liters. Oops. Divided by 4.0 liters. Things are getting a little crazy with my drawing here. So 1.50 liters there. Okay, divided by 4.0 liters there. And so I get a partial pressure of 0.38 times 1.5 divided by 4, or 0.1425 atmospheres of my gas A. And so that's, if my total pressure is going to be 0.49, then I already can figure out that my PB is going to have to be just 0.49, 0.49. Oh, let me write PB here. Is going to be 0.49, so P total, minus PA, which is 0.14. And again, my last sig fig is the 4 there. But I'll put all the digits in while I do the calculation. And so 0.4925, actually here. So carrying my numbers from last time minus 0.1425 is going to give me a PB of 0.35 atmospheres. And again, I could check this if I wanted to by doing the same calculation as I did for A. And I can plug in my P2 V2 RT over V total. So let's just see if that works out to be the same number so that our answer checks out. So now I'm just checking that PB equals 0.35. I've got P2 V2 0.56 atmospheres. times 2.50 liters divided by my V total, which is 4.0 liters. And lo and behold, that gives me 0.35 atmospheres. So yeah, the answer checks out. So we've got PB, we've got PA, which should only have 2 sig figs, and we've got P total, which are the things that we were looking for. And that's a wrap for Dalton's law of partial pressures. That's about all you'd have to do with it. And so I'll do one more video, which is on how all of this is going to change just a little bit if we take into account the behavior of real gases when they start actually kind of sticking together, or their volumes start to kind of matter in the total volume that we're looking at.